All right, I'm just restarting this whole lecture, and you just missed my 5 minutes of discussion on how to debug verilog, and all of that. Um, okay, so let's talk about homework 7. So you've got a traffic light. You've got 3 inputs. You've got 9 outputs. So this is some kind of state machine. You need to think about the state of the system. State is just sort of the status, the current collection of information about the system, the things that determine what mode it's in, right? And at one way of thinking, there's 9 outputs and there's 3 inputs. So worst case, you might think of 12 bits of state information. That's 4096, right? That's a lot of states. These car sensors are not part of your state. They're inputs. That's like X1, X2, X3 when we were doing state machines. So we don't need to think of those as inputs. But you will notice there's 9 lights. And so you might think, 2 to the 9th possible states. That's 512 states. Well, that's a lot of information. But the number of possible states is actually a lot fewer than this. So did anybody think about this in terms of how many different states there are for the traffic light controller? And what did you come up with? 3 states. All right. What are your 3 states? Red, green, yellow. Is that per lane or for the entire system? That's per lane. So if you do 3 per lane, 10 states for the whole system. Okay. I like that better than 512. Anybody find a number fewer than 10? Okay, 1 state would be all red. What are the other states? Green, red, yellow for each lane. Except, south could be red, and west could be red, and east could be green. 1 green at a time. So let's make a state table. So let me do west green, west yellow, west red, south green, south yellow, south red, east green, east yellow, east red. Alright, state 1, you said it's all the lights red. You can just focus on greens and put else statements for red. So that's close to what I'm after. So if a light's not green, it's red. Except, is it always true that if a light's not green, it's got to be red? There are yellows. Excellent. So there's something easier we can do than a state table. So at any given time, how many lights can be green? Just 1, right? So we could have west green, we could have south green, we could have east green. And if there's a yellow light, can any lights be green? No. So it's also possible that west could be yellow, south could be yellow, east could be yellow. And if we simplify this by assuming we're not going to make all the lights red, because that's not a terribly convenient traffic light if, you know, all the lights are red at some point, we can get away with just 6 states. And the states are simply the notion of which light is green or which light is yellow. And if we know, for example, that south is green, then we know west and east have got to be red. If we know that south is yellow, we know that west and east have got to be red. And so we really only need 6 states. And so that's a key realization to making this thing more doable. And so the other thing in this question is, in the Canvas write-up, it says for question 7, assume there's a 2 Hz clock input available to your circuit. So we have a clock signal, which is coming in with a 2-second period. Did I say 2 Hz? Okay, half a second. So 2 cycles per second. So the idea is, let's describe how the system moves from state to state based on these 3 car sensors. So we come in with west, south, and east. 1 equals a car, 0 equals no car. And we've got 9 outputs. So state machines in Verilog, there's usually 2 pieces. There's a piece that describes what happens when the clock ticks, and then there's usually some combinational logic that generates outputs. So let's just think about the clock tick part, how we move from state to state. So make yourself a state variable. Well, how many bits do we need to represent the state? Three bits, perfect. Right? We have 6 possible states, maybe 7 if you allow all red. To represent 6 or 7 different things, we need at least 3 bits, because 3 is 2 to the 8th. 2 bits would only let us represent 4 things. So make yourself a state variable. I'm just going to call it state, and it represents 3 bits. And I can just assign values like this is 0, 1, 2, 3, 4, 5. You can create parameters in Verilog. They're basically like constants, but you can also just, use magic numbers. And so when the clock ticks, what do we do? Well, there's a few options. So we can drive this from the inputs or from the current state. So, for example, if east, then there's a few possibilities. If east is already green, we don't have to do anything, because there's already a car, there's already a green light on east, and that's what we want to have happen since east has highest priority. So if east is green, we don't have to worry about anything. If east is yellow, we could change it back from yellow to green. That would be a little bizarre, but we could do that. But if any other light is green, say west is green, all we have to do is change our state to west yellow. So if state is equal to 0, set state equal to 3. If state is equal to 1, set state equal to 4. If state is equal to 2, we don't have to do anything because we can just leave things as they are. And if state is 5, maybe we'll not bother responding to this yet. And so you can do similar statements for if south. And so if there's a car to the south, well, if east is So if there's nothing to the east and there's something to the south. If south is green, nothing to do. If west is green, if state is 0, if east is green, state is 2, let's go to state 5. Make that east light change from green to yellow. If state is 5, meaning east is already yellow, let's change ourselves to state 1, which says now we're in the south green state. And then you can do something similar for if west. And we also need to make sure we go from yellow to red. So we can say if we're in state 3 and our clock is just ticked, let's go from west yellow to, well, we don't have to do that. We can drive it off these inputs. And if we use the system clock, it will be, a half second of yellow, a half second. Later it'll switch to green or red. But, we might throw in some counters so that we can slow down this clock. And, every time that we want to move from one state to another, we could add one to a 2-bit counter. And when it hits 4 or 0, when it rolls over, we could say, okay, go ahead and change from south yellow to east green or whatever. So I would say try to get east working first. Right? And so if east, if your state is equal to west green, then set your state equal to west yellow. This is pseudocode, this is not Verilog. Else if state is equal to south green, then state equals south yellow. Else if state equals east. If you're currently in east yellow, I'm okay if you just want to change it to green. Let's transition to red light. Yeah, except we don't have a state for red, so we would need to know which car is present that caused us to go from green to yellow. So to do this fully correctly, you would have an extra variable that when a car appears and it wasn't there before, set a variable to say, hey, which light is about to change green? Something like next green. And so if you're in state east yellow and next green was west, then go to state west green. If next green was south, go to state south green. But it's Monday. If you want to do this, this is, a little strange because you're sitting at a red light and the other light is green and it changes yellow and it's about your turn to go and all of a sudden a car shows up on that other lane and their light turns green again. That's kind of annoying, but I'm okay with that for this homework question. Alright, does that make more sense? The one of the tricks about this is, right, we're not doing anything with red lights directly. We're only focusing on who's green or who's yellow, and we know one of these will be the case. Again, we're not doing the all red case here, so it's just 6 states. And if you know which light is green or yellow, and you know which cars are present, you can pretty much from that decide what should the next light be. This doesn't handle the case if a car shows up and the light turns yellow and then that car goes away. But this is fine for a first order. Alright, so I guess my mic was off when I was talking about debugging Verilog in the beginning, so let me just summarize what I was saying. Verilog is tricky to debug, but there's two sorts of questions. The first is compile issues, the second is runtime issues. The compile issues, the compiler will usually point you to an error location, which may or may not actually be where the error is. So someone in chat suggested commenting out pieces of code to try to get your code to compile. That's a good strategy. It can sometimes lead you a little bit astray because commenting out a line may resolve a compile error that's not actually on that line. It could be on the previous line or the following line. But you have sample code, right? You've got sample Verilog code in all of these solved problems. You've got sample Verilog code in the textbook. You've got sample Verilog code in this Intro to Verilog Programming. And so one way to write Verilog when you're learning it is start with a piece of code that works and change it, right? So take some sample code and I'm not saying just blindly modify this to change this into that, but for the sake of this statement and the module statement and the inputs and outputs and the wire and the reg and all that, find a piece of code that works and use that, right? I think when I was learning Verilog, I had one module I just used every time for a few weeks. When I learned Java, I had one .java file that I knew worked, and I always started with that and used it kind of as a template for memorizing and getting used to the things we do all the time: module space, module name, parentheses, comma separated list of ports, close parentheses, semicolon, new line, that kind of stuff. The runtime errors can be tricky also, but you can always add output ports. And so if you've got some circuit and I've got this notion of state, for example, I can make state an output of my circuit, right? Now that's not normally the case, but if I make it an output port, then I can go ahead and I can throw up some timing diagrams for it, and I can see what my state variable is doing. If I have a variable like next green light to tell me which lane is supposed to turn green after the current yellow light is done being yellow, I can make that an output. And I can look at that. And so this is kind of like adding print statements in the middle of your code. It's a way to see what's going on with your internal variables, and that can help you with debugging. All right, let me talk about question 8. So question 8 is asking you to implement an ALU which adds, subtracts, and multiplies. We haven't really talked about ALUs yet. They're discussed in chapter 9 of the text. But an ALU is just an example of a more complex combinational block. And so here's a block diagram for an ALU. An ALU is an arithmetic logic unit. So it's one of those central parts of a computer, a CPU. So we might have two inputs going in. We might have an input A, and remember this slash with a number on top means this is actually 8 arrows. So this is an 8-bit number. And we'd have another 8-bit number B. And we have some output value X, and we don't know how many bits that is. But this is a block of logic that can do different things to A and B. For example, it can add them, it can subtract them, and it can multiply them. And so we need to have some sort of input saying what function we want to perform. Well, our ALU can add, subtract, or multiply. How many different, how many bits do we need to represent those 3 possible choices? Two bits, perfect, right? 1 bit would only let us represent 2 possibilities. 2 bits will let us represent 4 possibilities. So we'll make this 2 bits. And how many bits do we need for our output? I mean, it's kind of up to us because we're designing this thing, but if we were trying to make this like, you know, the best ALU available that everybody would want to use, how many bits will we want for the output? Uh, 1024 bits would be a lot of bits, but I know what you're trying to say, I think. '64 is closer. So if you add two 8-bit numbers, how big is your sum? How many bits? So if you add two 8-bit numbers, your sum's going to be something that fits in 9 bits. But if you multiply, you're right, it's 16. So if we wanted to be able to multiply really large 8-bit numbers, we'll want 16 bits on the output. And yeah, for addition, adding two 8-bit numbers, you get 8 bits out. But if there's a carry, you get a 9th bit out. So 16 bits will let us do, you know, two large 8-bit numbers added or subtracted without losing any information, and 16 bits would let us multiply two large numbers, like 255 times 255. And this is verilog. We're not going to write truth tables for this, so there's very little harm in making this big. All right, so what does our function do? Well, you know, we got 2 bits, so we got 4 possibilities. And so maybe, you know, I'll say if my function inputs are 0, 0, my output's going to be a plus b. If my function is 0, 1, my output will be a minus b. If my function is 1, 0, my output will be a times b. I'll do a cross so it's not an and. And if my function is 1, 1, I don't know. You could either leave that blank and say, hey, this is unspecified, or you could add some fancy fourth function. You could output a 0, you could output a -1, you could output the largest of a and b, and you could try to do division. The problem doesn't ask you to do anything in that case. You only need these 3. So this would be an example of a function table. But, you know, this could be subtraction, multiplication, addition, doesn't matter. But you got to specify somewhere in your answer what the function does. And now this is pretty much 3 lines of verilog code. And so don't undervalue the use of this question mark operator. This is sometimes called interrogation or a ternary operator in C, and it's very useful for assign statements. And so I could do something like assign x equals, well, suppose all I had was addition or subtraction. I could say assign x equals function equals 0, question mark a plus b, colon a minus b. And so this question mark operator in general, if you say something like some condition, something colon something, this is equivalent to A if your condition is true. Otherwise, it's equivalent to B. So this statement is just a slightly cryptic way of saying, hey, if function is equal to 0, all of this is equivalent to the expression a plus b, which means this statement says assign x equals a plus b. So if function is 0, it will set x equal to the sum. If function is equal to 1, it would set, if it's not 0, it would set x equal to a minus b. And so I could do something like this. Assign x equals function equals 1, x1 colon a times b. Alright, so if my function is equal to 1, I'm going to set x equal to the the result of this, which is a minus b. So that takes care of that. Otherwise, if function is not 1, I'm going to set x equal to... actually, let me do this. Alright, if function is equal to 2, I'll set x equal to a times b, which is what I'm after. Otherwise, I'll set x equal to whatever I got up here, which is going to be either a plus b for 0 or a minus b for 1. And so there's a pair of assign statements using this temporary x1 that should set x equal to which of those functions you want. You can do this in one line, and if you've ever done any sort of cell programming in Excel with their if statements work the same way as this ternary operator. And so you can start nesting these things together and make all these really long, complex looking expressions. So one thing to notice is that, for all of the complexity of this will be a really complex circuit. A multiplication is a complex task. This is still a combinational circuit. There's no clock, there's no notion of state. We could write a truth table for this, but it would have 18 inputs, right? That's 250,000 rows in your truth table and 16 outputs. So, 4 million ones and zeros in your truth table, right? We wouldn't want to do that by hand, but verilog, right, it's going to end up being a couple of assign statements. All right, other homework questions. Bye. Have a good day.
Bye.
How do you want us to turn in the homework? So the homework did not explicitly ask for a timing diagram. I suggest if you feel like your code is working correctly, it's probably because you simulated it. I would say go ahead and put a timing diagram in. And so your code, copy and paste it, right? If you do a fuzzy screenshot, I can't grade it. But you can copy your code from the LDEC tool and then just paste it as text into your Word document or Google Doc or whatever you're using. If you change the font to something that's fixed spacing like monospace or Courier, it'll line up nicely and so on and so forth. But copy and paste the code in. If you're going to include a timing diagram, just do a screenshot of the LDEC window. So use a snipping tool in Windows or the print screen button in Linux. For the lab, you need to include timing diagrams for each experiment. So copy and paste from the window of your waveform analysis. All right, and I'll talk about the labs in a minute, but while we're on the subject of ALUs, let's go ahead and talk about ALUs. For our explanation for the lab, how in depth do we need to go? If it took you, 30 minutes to understand what the question was asking you for, I would expect at least a few sentences explaining your understanding of what the lab is supposed to do. So with these labs, you can always assume that the person reading the lab understands the material up to the point of that lab. So you don't have to teach the reader what verilog is. You don't have to tell them what a module statement is. But the person reading your lab report, experiment 3, here's a shift register. Well, what does that mean? What am I expecting this circuit to do? Experiment 4 is a 5 of 16 detector. What am I expecting that to do? Right? turn on a 1 when 5 inputs are 1. Well, what exactly does that mean? I've gotten a bunch of emails over the weekend asking for clarification on that. So you should put something in your report. It could be 1 or 2 sentences describing in your own words what this circuit is supposed to do. And then, you know, if your understanding was different from what the intent was, and your verilog code is therefore different from what I was expecting, at least I can see if it matches up your understanding, right? As opposed to this code does nothing like what it's supposed to do. And you can assume the person reading your lab, you know, like I say, has a basic understanding of the general subject matter, but not of the lab itself. So you've got to describe in your write-up, you know, this is a circuit that will generate a 1 output when there's an even number of zeros, or whatever, for the parity generator. And normally, you know, I would say you can show me your lab and say, hey, is this a good enough description, and so on, but not at this point, because, you know, we're like 15 hours from when the lab is due, and I can't field questions like that today. But normally, you know, if you write your report up a few days before it's due, you can totally submit it and say, hey, I just submitted my lab. Can you take a look at my explanation for experiment 3 and see if that's reasonable? And I'm fine with giving you feedback like that. That was the other comment I made when you couldn't hear me about debugging, is like, you know, your other option for debugging is always come by lab hours, come by office hours, and screen share your code. And I'll do my best to not just, you know, say, oh, change this, but to try to help you find what the bug is, right? To try to help you understand why what you thought was going to work ended up not working. Either gave compile errors or gave the wrong behavior, right? And we can do that if we're screen sharing, and you know, I can say, well, add an output for this, and let's look at the timing diagram. So why do you think that signal is changing from a 1 to a 0 at this point, right? And we can go through that process. And I think that's your best bet for not just learning how to debug, but for learning how to, you know, avoid bugs in general. No, Lab 7, Homework 7, those are the end. We got no time left. We got 1 class after this, so and since I moved deadlines to midnight, I won't get to grade your homework or lab until Tuesday, and I can't guarantee I'll get it graded by Wednesday. But when I turn back when I give you grades in Canvas, if you lose points, I always post comments explaining why you lost the points. So please look at those. And there's still office hours on Thursday and Friday, and I'll almost certainly get your homework back to you sometime on Wednesday. But if it doesn't happen before class, read the comments and then come to office hours, lab hours, ask questions. Hey, I don't understand why this didn't work, right? Why did I lose points here? Why did you say this wasn't valid syntax, or whatever? Because you'll probably see a verilog question on the exam. Not a lot of points, but, you know, probably a 10-point question. All right. Let's just take a look at ALUs. So if you go to component specifications on ENGR250.com, there's an arithmetic logic unit, ALU. This is just an example. This is a popular device. And so 20-pin device. It's got a series of A and B inputs, and you can read the taglines on this. Fully parallel 4-bit ALU, 20-pin package. Arithmetic and logic operations selected specifically to simplify system implementation. A minus B, B minus A plus B, and 5 other functions. Well, here's the function table. Thanks. So this ALU can do 8 different things. And so we have a 3-bit function input, and depending on those 3 select lines, this is what the ALU does. And so there's inputs A and B. Thank you. And there's an output, which is presumably S0, 1, 2. Nope, that's the select line. F0, 1, 2, and 3 are the function output. And so, if you put your 3 select lines to 0, the operation is clear, while your output's going to be all zeros. If you put your inputs to 0, 1, 0, the output will be A minus B. So you can subtract in both directions. You can take the sum. You can do an XOR. You can do a logical OR, a logical AND, which are presumably bitwise. And you can set the output to all ones. And this block also has carry outputs and carry inputs, so you can cascade them. Just like your 1-bit full adder has a carry in and a carry out, well, this 4-bit circuit has a carry in and a carry out, which can be used to, take this and turn it into, say, an 8-bit adder by using 2 of these side by side. And so there's more detail on exactly what this does for A and B. And there's the circuitry. So a nice complex circuit. But you could implement this in Verilog using the same idea as what we're doing for homework 8. Just more function options. System diagram, or logic symbol, 3 select bits, a carry bit going in, 4 bits of A, 4 bits of B, 4 output bits, and then depending on the exact model, 81 or 82, you might have an overflow and an outgoing carry bit, or you might have what are called propagate and generate bits coming out. We probably won't get to those in this course, but if you do another course in computer architecture, you'll learn about fast addition and circuits that are used for adding numbers together very quickly. We might get to it today. We'll see. Alright, so that's an example of a larger real-world ALU. The ALU we're doing in here is a simpler version of that, 3 functions, but 8 bits instead of 4. Alright, let's talk about Lab 7. So, 4 experiments. First one is the even parity generator, and we talked about this a little bit last week. But the goal is to output a 1 if there's an even number of 1s. Otherwise, output a 0. So if you only had 2 bits, an even number of 1s, it should output a 1. So it would output a 1 here. If there's no 1s, that's 0, 1, 0 isn't even.
Professor, we can't see the paper.
Thank you. So if there's 2 1s, that's an even number. The output should be 1. If there's no 1s, 0 is an even number, so the output should be 1. And in these cases, the output should be 0. And this is an exclusive NOR gate. If you drew this in a K-map, you'd see that checkerboard pattern. And so if we do one more case explicitly, an even number of 1s would happen right here, 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 and here. And be 0 on those. And this you may recognize from your work with adders. with the full adder. But if you K-map it, you'll see that checkerboard again, and this will actually turn out to be an exclusive NOR of all three of those. And so the hint in the question said XOR is helpful. Well, this is why it's helpful. Because if I have 8 inputs, all I have to do is XOR each of those with the others and then complement the output. And verilog, you can use that as an exclusive OR operation. Remember, a pipe is OR, an ampersand is AND. This will do an XOR. So this is a one-liner. Take your 8 input bits, XOR them all together, throw a tilde in front, tilde is a not, and put that in an assign statement. And that gives you a parity generator. Experiment 2, 8-bit up-down synchronous binary counter. So the up-down part is the idea that this counter can count up or down. So we've got 8 bits coming out. We've got a clock. Since we're doing verilog, we're going to want to reset so that the simulation doesn't, say, I don't know what the value is. So we have a reset input. But then we have one other input. And so I've been suggesting to people that maybe you call this up. And the idea is up equals 1. It counts up. If up equals 0, it counts down. And depending on whether this is a 1 or a 0, each time the clock ticks, meaning changes from 0 to 1, the output either increments or decrements. And so to test this, you can set up to 0, hit the reset line for a few clock pulses, bring the reset line low, so let's say 1 equals reset out to 0, 0 equals don't reset. So drive the reset line up in the beginning, then bring it down low. You can use a formula stimulator for that, and keep the clock ticking every 20 nanoseconds or something. And if up is 0, you should see your count counting down. And in the LDEC tool, you can change the radix. So if you don't like hex, you can count from, 255, 254, 253, and so on. And then, somewhere after a few hundred nanoseconds, raise your up input to a 1. And now the count should start going up. And you can choose how to stimulate this. You could change this randomly every 100 nanoseconds. You could use a clock. You could use a formula. It's up to you. But that will let you test the behavior of this circuit. So the lab assignment says 8-bit up-down synchronous binary counter. So synchronous means everything happens when the clock ticks, including the reset. 8 bits on the output and up-down. And one notational thing that's worth mentioning here, sometimes on a circuit, you might see this input written something like this. Up/down bar. Or you might just see it written as down bar. And when you see a name with a bar on top of it, that basically means that signal is active low. We think of this as an input that's going to get inverted, right? If this is an input of 1, then the not down signal is asserted. Well, if we're asserting not down, we're asserting up. If the down bar input is a 0, then not down is false, which means down is true, so this is counting down. And sometimes if the people making the data sheet are really kind, you'll see both of these. And it tells you explicitly, once you know how to read it, hey, if this is a 1, it's going to be an up counter. If it's a 0, it's going to be a down counter. All right, experiment 3 is a shift register. We talked about this before, but let's talk about it again. 16-bit shift register using verilog. And let me go ahead and actually, let's build this. I'm going to try sharing from my other screen again. All right, let's see. All right, so hold on one sec. All right, I think this will work. Can everybody see my screen?
Yep.
Cool, thank you. All right, so let's make a short shift register. So let's make a new workspace, and I'll call this shift. And I'll still call it shift. And I'm going to right click and say add a new verilog source. And I'll call that shift. Alright, so what are our inputs? We're going to need a clock input. So that's going to drive the whole system. We're going to need an input bit, which I'm just going to call in. And I'm going to make an output bit, which we're going to call out. So let's make a 4-bit shift register. So the idea is each time the clock ticks, we want to take a sample of the input and we want to remember what it is. So we've got all these ones and zeros coming to the input. We're going to ignore them until the clock ticks. And at the moment of the clock tick, we want to say, hey, I see a 1, okay, you get to go in line. We're going to load you into the shift register. And we're going to remember that bit value. And the next time the clock ticks, if we see a 0, we're going to say, okay, we're going to load the 0 into the shift register. And we want to remember, in this case, the last 4 bits that we've seen. So we're going to move them down a set of flip-flops. We're going to take one bit value and we're going to move it into the next flip-flop when the clock ticks, and make space in that first flip-flop for the new bit that's coming in. And the last bit, it's in the last flip-flop when the clock ticks, that's going to disappear. That's going to go away because we're only going to remember the last 4 bits of input. Alright, so let me try this. So I'm going to make this register of 4 bits called data. The new bit is going to get stored in data bracket 0. So I can call this anything I want. I could just call, 4 registers A, B, C, D. I'm going to make an array called data. Data bracket 0 is where I'm going to store the new bit. And data bracket 3 is going to be the oldest bit. Alright, so I'm going to say always at the positive edge of the clock. And what I'm going to want to do is shift my register. So I can do the following. Data bracket 0 gets assigned whatever the value of input is. Data 1 gets whatever the value of data 0 is. Data 2 gets assigned whatever data 1 is. And data 3 gets whatever data 2 was. The old value of data 3, there's nowhere to save that. That's just going to disappear. So there's the whole shift operation. And our output from this circuit, this out signal, is always whatever the value of data 3 is. It's that last bit that we're remembering. That's the delay part of a shift register. And so I'm just going to do an assign statement. Assign out equals data bracket 3. So this is a 4-bit version of what you did in Lab 6 with your experiment 1 when you made a delay circuit out of 2 D registers. That was a 2-bit shift register. And so this should compile. And then we'll do file new waveform. And we'll initialize the simulation. We'll choose the top level module. And now let's see what the simulation does. So my clock, I'm going to right click, set stimulus, and I'm just going to make this a 20 nanosecond clock. And my input, I'm going to set stimulus and I'm going to make this random. So I'll pick a random value. I'll change every 20 nanoseconds. And I'll just put some arbitrary seed in here. And let's see what this does. lost my little... So I'll just use F5 to run this. So I hit F5 a bunch of times to run this. I'm going to scroll wheel to take this out. And from this view, you can see the delay effect of this, right? Here's our input, which is random. Here's our output. And our output, this bottom trace, looks just like the input, except it's shifted over in time. In particular, it's shifted over by 80 nanoseconds. Right? This edge is occurring at 160. Sorry, yeah, 100. Well, let me do this one. This edge occurs at 240. This edge occurs at 310. It's a 70 nanosecond. That's interesting. But it's 4 clock ticks. So this is the delayed version of the input. Now, if we drag the actual contents of the shift register over, and let's run this further, and let me rearrange these. Oh, I can't rearrange them. So here the input is going high. We've got a new pulse coming in right here. And on the next clock event, that gets loaded into data 0. And then the next clock ticket moves into data 1, and then data 2, and then data 3, which is when we see it in the output. At this point, the input went low, and a little bit later, that low signal made it into data 0, right here, and then it made it into data 1, and then data 2, and then data 3, which is where we saw it on the output. So this is your basic shift register configuration. And you want something like this, but 16 bits for experiment 3. And when you test this, you should see similar behavior where an input appears on the output, but it will be delayed by 16 clock ticks instead of 4 clock ticks. And so I mentioned briefly before this notion of using this less than sign followed by an equal, and I said that was a non-blocking assignment. If I make a mistake and I do the following, if I leave off my arrows and I just use an equal sign, this will compile just fine. And if I end my simulation and initialize my simulation and set this as active and start F5ing, I get a really different behavior. Right? Every time my input changes, my output follows it 1 clock tick later. And you can see that all 4 bits of my shift register are always the same. And so this is not doing that delayed behavior that we want. This is not doing this business of take your input and move it through from one register to the next until it gets to the output. All 4 flip-flops are taking on the value of the input each clock tick. Right? I broke my shift register. And I did it simply by changing these from less than equals to just equals. Alright, let's do a 5-minute break. and I want to come back and look at why this is happening, and I want to look at this bigger notion of thinking about the circuit that your verilog code describes, and then we'll talk about experiment 4 in the lab, and we'll go on from there. So let's take a break. Let's come back in about 5 minutes at 9:20. All right. So let's talk about what this verilog code is actually doing. So if we think of this code and change it into hardware, let's just look at that shift register. So always at positive edge clock. And so we did something like, data 0 comes from in, data 1 comes from data 0, data 2 comes from data 1, data 3 comes from data 2, and then assign out equals data 3. So the idea here is we've got a clock, and so we've got some flip-flops somewhere that are being ticked with this clock. Since these are all using this less than or equal sign, we're saying don't block. Don't wait for this to finish before we do this. Do them all at the same time. In other words, be parallel. So we have 4 flip-flops. And their clocks are all being triggered by the same signal. Clock. And this statement is saying, hey, we want when the clock ticks that this first flip-flop, D0, should be set equal to whatever the input is. So it's going to build a circuit where the input just goes into the D input of this flip-flop. And it may be a T flip-flop or a JK, who knows what the compiler is going to come up with, but we can just think of these as simple D flip-flops. And the second statement says, hey, take whatever the value of D0 is and load that into D1. Well, the current value of D0 is stored in this flip-flop, and this statement says when the clock ticks, take that value which is coming out of Q and load that into bit 1 of this register. Well, we do that by sending this to the D input. And the same thing here, and the same thing here. And this assignment statement says, hey, let's take the output of this flip-flop number 3, this last flip-flop, and let's send that to our output. So when you compile Verilog code, this is sometimes called synthesis. And the idea is, let's create a piece of hardware based on the Verilog. And so this is the circuit that might be synthesized from this set of code. And it's a 4-bit version of Experiment 1 Lab 6. Now, if we take off those less than signs, something very different happens. So always at pos edge clock. So we say D0 equals in, D1 equals D0, D2 equals D1, D3 equals D2, and then assign out equals D3. Alright, well, we have a flip-flop. We have a clock signal. And input definitely goes into here. And here's the output of D0. Well, this code, since we're using just equal signs, these are what we call blocking assignments. So the way the compiler interprets this is, hey, when the clock ticks, first I want to take the input and copy it into D0. So it builds this piece of circuit. And then after I've done that, I want to take the value of D0 and I want to set D1 equal to that. Well, D1 is going to be equal to, whatever value was loaded into D0. So this is going to take this and send it to D1. And then D2 is going to set equal to whatever D1 is equal to. So this is just going to take this and send that to D2. And then D3 is going to set equal to whatever D2 is. Well, D2 is coming off of this line, so this will be D3. And then our output should be equal to D3, so this will go to our output. So this code will synthesize a circuit like this. And it's a very different behavior from this, which is our nice shift register. Things move through one step at a time. This is a single flip-flop that stores one bit when the clock ticks and then sends that bit to 4 different locations. And so that's why when we look at that timing diagram, we see all 4 bits of our data register changing in sync. It's because they're being driven from the same flip-flop. So usually when we say reg, R-E-G, for a variable, we get a flip-flop, but not always. Sometimes our code will actually synthesize into something that says, hey, we don't actually need 4 flip-flops, even though we have a 4-bit register, because I know that these values are all the same as the value of D0. So this is another sense in which, trying to think about what the hardware looks like that corresponds to your code can be important. Alright, so experiment 4. Experiment 4 is the 5 of 16 event detector. So, I don't know, you've got people walking into a line at an amusement park, and this is for a roller coaster, and your roller coaster needs the weight of like 11 adults and 5 children, right? And if it's got exactly 11 adults and 5 children, then something happens, otherwise something else happens. So we've got a line that is recording each person coming into this queue to tell us whether they're an adult or a child, right? And if there's an adult, we're going to record a 1. And if there's a child, we're going to record a 0. And the goal is, at any point in time, we want to know if we've got exactly 5 events that we've recorded. So here's your clock. The clock just keeps running. And each time the clock ticks, we want to look at our input, and we want to record it. So let's say at this point we saw an input of 0, and here we saw a 1 and a 0 and a 1 and a 1 and a 1 and a 0 and a 1 and a 0 and a 0 and a 1. Alright, we have to get this thing started, but assume it's been running for a while, and just to suppose we've seen nothing but zeros so far, and now we're starting to see 1s. Alright, at this point, over the last 16 events, we've seen a single 1. Our output is still going to be 0. At this point, we've seen 2 1s, 3 1s, 4 1s. At this point, we've now seen 5 1s. 1, 2, 3, 4, 5. Our output's going to go high. At this point, over the last 16 events, we've still seen 5 1s. Our output is going to stay high. At this point, we've still seen 5 1s. Our output is going to stay high. At this point, we see another 1 coming in. Now, over the past 16 events, we've seen 6 1s. The output goes low. Eventually, if these are all zeros after this, at some point we will be 16 events past this moment, and this 1 will disappear from our shift register, and at that point we're going to have 1, 2, 3, 4, 5 1s. Our output is going to go high again. Alright, so every time the clock ticks, you look at the input, you remember it. And at every moment in time, you look at the last 16 events you've remembered. If exactly 5 of them are 1, the output is 1. Otherwise, the output is 0. Okay, that's the exact description of what your circuit should do. And so system diagram might look like this. 1 bit goes in, 1 bit comes out. And the clock, which is just, you know, bouncing up and down, up and down, up and down. Alright, so it's not 16 input bits, and you just count up to see if you've got 5 ones. And it's not input 16 bits, and then decide whether to output a 1 or a 0. And then input another 16 bits and decide whether to output a 1 or a 0. It's a constant, ongoing operation. Every time the clock ticks, remember that new bit, forget the bit that came 16 ticks ago, and at any moment, if the last 16 events had exactly 5 ones, your output should be 1. Otherwise, your output is 0. And so how do you do this? You can use a shift register. So in the 4-bit example, every time the clock ticks, we record the new bit over here and we shift our bits over. So let's do a 2 of 4 detector. So 2 of 4. So our output will be 1 if exactly 2 of the last 4 bits that we've seen are equal to 1. I'm going to get in trouble trying to draw this out. Let's see. I already closed out my LDEC tool. That would have been a great way to do this. Alright, so let's set our input high. Alright, so here's our timing diagram. This is a 2 of 4, so we're going to have a 4-bit shift register. So let me try to make our timing diagram. So the clock ticks. This bit value will get stored in data 0. And the next time it'll drop, and the next time it will rise, and the next time it will drop. Alright, data 1 is going to reflect the previous value of data 0. So at the moment where this, let me change the input back just a little bit. At the moment when the clock ticks, D0 was 0, so D1 will be 0. But at this clock tick, D0 is a 1, so this will be a 1. And so we're going to get this delayed version of D0. And then D2 is going to be delayed a little more. And then D3 will be delayed another tick. All right. So how do we know if 2 of our last 4 events have been equal to 1? Well, our last 4 events are always stored in these 4 bits, right? These 4 register bits show us the last 4 events. So for example, right here, I can say, hey, during all of this time, I had 2 events that were 1, and the 2 events before that were a 0. Right? The fact that this is a 1, a 1, a 0, a 0, that's 2 of my last 4 events were a 1. And so my output should go high. When I get over here, I've got 1, 2, 3 of my last events were a 1. Well, that's not 2, so my output should be low. So my output's going to look like this. At this point, I've got 0, 1, 1, 1. I've got 3 events that were 1, so that's going to stay low. At this point, I've got 1, 0, 1, 1. That's 3 events, so that's going to stay low. At this point, I've got a 1, 1, 0, 1. That's 3 events. That's going to stay low. At this point, I've got a 1, 1, 1, 0. That's 3 events. That's going to stay low. At this point, I've got 0, 1, 1, 1. That's going to stay low. At this point, I've got a 0, 0, 1, 1. Now I've seen 2 of my last 4 events were a 1. My output's going to go high. And at this last point, I'm going to see a 0, 0, 0, 1. I've only seen 1. My output's going to go low. So this is reflecting the fact that on this clock tick, I had an input of 1. On this clock tick, I had an input of 1. That was 2 out of 4. At this clock tick, I've seen 3 events. That's the 4th one, and then my input is 1 again, and so I'm still going to have seen 3, and so on. So how do I generate this output from these flip-flop values, these register bits? Well, one easy way to do it is just add these together and see if they're equal to 2. If I add these together, this is 0, 1, 1, 1, and I get a 3, that tells me 3 of my last 4 events were equal to 1. Well, it's not 2, I want my output to be 0. But if I add these together right here, this is a 0, 0, 1, 1, 0 plus 0 plus 1 plus 1 is 2. I've seen 2 1s out of my last 4 events. And so I set my output equal to 1. So this is an assign statement. Add up the bits of your shift register. If it's equal to 2, set your output equal to 1. So you can use that ternary operator and assign out equals, this plus this equals 2, question mark 1 colon 0. So that's for a 2 out of 4. Same thing for a 5 out of 16. You need a 16-bit shift register. Guess what? You got that from experiment 3. Your assignment statement's going to be longer because you have to add 16 numbers, but it's verilog. It's just, 16 of these with plus signs in between. And it will figure out how to make hardware to do that addition. Alright, does that make some more sense? Alright, I'll take that as a resounding yes. All right. One more thing we can do with this ALDEC tool that's kind of useful. We can play around with timing in a little more detail. So let's take a look at a circuit that has a glitch in it, and just kind of see how we can reveal this with Verilog. So I'm going to build the following circuit. I'm going to take an input A, and I'm going to run this into an AND gate. And I'm going to generate an output X. And I'm also going to take A and run it through an inverter and feed that into my input. And so if we did an analysis of this circuit on paper and we tried to write an equation for X, X would be equal to A ANDed with A bar. And so A is either a 0 or a 1, A bar is the opposite, and the AND of these two is always 0. So from our truth table, it looks like the output X should always be equal to 0. But let's go ahead and simulate this. So let me do my goofy screen share again. Get rid of this. Alright, so here's our ALDEC tool. Let's go ahead and just build a Verilog module. So I'll say new workspace, and I'll call this glitch. Make an empty design. We're going to use Verilog. Glitch. We'll do a right click, file new Verilog source. We'll call it glitch. So our circuit has a single input, which is X, and it has an input A and an output X. Alright, so I'm going to make another wire called A bar. And I'm going to call A bar, I'm going to make it an output actually. So make A bar an output, and I'm just going to assign A bar to be equal to not A. And then I'm going to assign X equals A and A bar. So we can compile this. We can do file new waveform. Initialize our simulation. Select our top module. And let's stimulate A with a clock. And we can go ahead and do, let's do 30 nanoseconds. Let's do 40 nanoseconds. And let's go ahead and run this simulation. So you can see what's happening here, right? A is changing from 0 to 1 back to 0. A bar is the opposite, and X is equal to 0. So that looks fine. Let's change our code just a little bit. So in Verilog, we can introduce delays. So using a number sign, we can introduce a timing delay. So when I say A bar equals not A, in the front of this assignment statement, I'm going to say number sign 5. So that number sign 5 says, hey, this inversion operation, this assignment to this variable A bar is going to take 5 nanoseconds. So I'm introducing a more realistic version of this inverter and saying, hey, there'll be a 5-second propagation delay between when the input changes and when the output becomes the complement of the input. And I'm going to add another delay on the AND operation. And I'm going to say the AND takes 2 nanoseconds to do its thing. So this is just saying, you know, these operations are not instantaneous. If A changes 5 nanoseconds, the inverse of A will get assigned to A bar. And if A or A bar changes 2 nanoseconds later, X will get changed to the new AND of those new values. So we can compile. And let's go back to our waveform and initialize it. And let's set our stimulus as active. And now let's run our simulation. And you see something different happening now. So when the input A changes from, say, 1 to 0, the inverse A bar takes a little while to respond. Right? It's in particular, it's a few nanoseconds later that A bar arises. And so our output X is no longer just 0. X actually has these little glitches. These are non-zero periods of time during which X goes high, even though according to our truth table, X should always be 0. So this is unexpected, undesired behavior. And it's just a consequence of the realities of these timing delays. And so we analyzed this circuit a few weeks ago and saw this on paper. But we can use these tools like, you know, LDEC with its simulation capability to, you know, test our circuits and see these kind of timing glitches. And it's a whole lot easier to detect this and manage it at this point of things than after you've sent, you know, a design to a foundry and waited, you know, a couple of months for your prototype chips to come back and you find out, hey, we've got a glitch in the system. There's really not a lot of editing you can do on silicon these days. You basically throw it in the garbage and go back to the drawing board. So this is another way that simulation is useful. And the fancier tools will, you know, do different timing scenarios for you and try to detect these kinds of glitches or race conditions, situations where the output depends on how quickly signals pass through different parts of your circuit and so on. So that's just kind of a fun way to sort of see something through this tool that can otherwise be kind of elusive. All right, we're at 9:50. I'll call it quits here. That's it for new material for the course. So Wednesday, we'll just talk about whatever questions people have, logistics for the final exam, and I'll just kind of do a run-through of topics from start to finish. But if you have questions, please bring them, and let's talk about them in class. Otherwise, I'll just ramble on for 2 hours and rehash the past 10 weeks of the quarter, which will not be very exciting. So one way or another, I'll see you on Wednesday. And yes, verilog will be graded gently. This is a topic you can spend years getting proficient at. I'm looking for low-hanging fruit here, right? So do the best you can. Get this turned in on time. I'll try to get it back to you sometime Wednesday, and we'll talk about it from there. All right, thanks. Have a good one, everyone. See you next time.
Mr. Messias,
Yeah.
I noticed that you said that your 270 class in the summer would be taught in person. Does that apply to the fall quarter for like your CSE classes for discrete structures and programming tools?
So